Swayam Prabha. Digital India. Educated India.
Last time we had done it by looking at this tables, that if this is minus, it means that the values are minimum of the plasma flow rate will give you maximum of the Logit efficiency. Here instead we have done the actual calculations and found it out. So, this way also you can do it, this way it becomes very clear, particularly with respect to the interaction. And then comes that this results that we have got, we must validate. It means that we must carry out a few experiments by keeping plasma flow rate at low level, additional gas flow rate and feed rate also at low levels, but RC length at the highest level, and of course carrier gas flow rate at a high level. Conduct a few experiments and see that it gives you the maximum possible efficiency, Logit transformed efficiency. Logit transformation is also increasing function, and therefore, if the Logit transformed efficiency is high, the efficiency is also high. So, we must run a few trial at the recommended factors and level for maximum efficiency, and we should see that the efficiency value should fall in the predicted 95% interval estimate of the maximum efficiency. So, let us do the interval estimation. So, this is the model we have estimated. Expected value of y, it is actually Logit transformed y, is this. This is the coefficient, and these are the red values which are shown as having the coefficient, they are written here, and these are the actual parameters which we have put in here. And if you take you remember that this is a coded one. So, therefore, plasma flow rate at minimum is going to be -1, this is going to be -1, reaction chamber length is the highest, so it is going to be +1. This is not the values that you have calculated here, please remember these are the coded values. I think we must write it down here. These are all for coded values, very important, this is for coded values. So, this is going to take -1 value, this will be -1 because we have to keep at minimum, and this will be +1 value, this will be -1 times -1, this will be also -1 times +1, and this will be also -1 times -1. Okay, this is how you have to calculate. So, this is what I have shown here. This is what you have to keep these values, and then these are you have to do it in a coded value. So, these are the values you will take, and then how do you find the range? The range is found in this manner. This is your f value and adjusted mean square is your f value is that value at 90. Here something I have not written, I must write it down here. This is f, it does not show well, let us change the ink color, it shows f at alpha. Please remember we have to take it at alpha level, and therefore, you take f at alpha 95%, that is 0.05. This is the error variance which is shown here, and then this is the so this is going to be the effective number of replica, which is total number of experiments divided by degrees of freedom of selected factors plus 1, R is the number of validation trials. So, accordingly if you calculate, we were to calculate 4 validation trials. So, the Logit efficiency interval is this. Interval estimate for efficiency for 4 validation trial is 80% to 96%. These are the 4 validation trial results, which is 92%, 89%, 90% and 87%, and the average of that is 89.5%, which is very much within the interval, and therefore we can say that our results are validated. In other words, this model is the correct model in which you select only, here is the model, only Logit efficiency described in the form of plasma flow rate at the lowest level, additional gas flow rate, this is the, plasma flow rate kept at a low, additional gas flow rate kept at low level, feed rate kept at low level, and reaction chamber length kept at high level with carrier gas flow rate at high level would give you the highest efficiency of the system, and we validated it by going through the finding out the 95% interval of predicted value of 4 validation trials, and the design is validated. Hello and welcome to the course on dealing with materials data. For past few sessions we are going through the application of design of experiments for metallurgical applications, and we are learning it through the case study on optimization of production of nano titania powder through microwave plasma synthesis system. So, let us review. We found that when the response is in a percentage, has a limited range in when it varies from 0 to 100 only, to meet the assumption of normality of error, we have to make a Logit transformation of the response variable and carry out the analysis through with the Logit transformed response. Then we talked about how to estimate the prediction interval. We of course worked out how to find the factors that are important by conducting hypothesis testing, that regression parameter beta I is equal to 0. Then looking at the t values and the p values, we can decide whether we have to reject the hypothesis or accept the hypothesis. Here rejected hypothesis is of importance because that says that that factor is important in this predicting the efficiency of the system. So, now you see the importance of rejection region, because rejecting the hypothesis gives us lot of information compared to accepting the hypothesis. Accepting the hypothesis says that that particular factor has no effect, but when you reject the null hypothesis, you come to know that that particular factor has an effect on the response value. So, we looked into the tables and then we also looked into the analysis of variance table to understand lack of fit. Because of the two replica, we could find out if your the experiment, the model has any lack of fit. Our again hypothesis was there is no lack of fit, and we in this case we accepted the hypothesis, and therefore we can say that there is no lack of fit in the hypothesis. You remember there were two responses. So, this time we want to continue the same process with the response of percentage anatase, and remember now we are wiser people. So, since anatase is also in a percentage value, we are going to take its Logit transformation and then do the analysis, and then we have the validation trials, putting the two responses together, and we will come to the final conclusion for this particular case study. So, let us start. Here this is the table for estimating the effect of each parameter using T distribution for Logit transformed anatase, percentage anatase. So, we are wiser now, we have already done the Logit transformation of percentage anatase response, and then we are doing the analysis of the data. And here what we find is that again we are giving the, this is an important, I am sorry, I should have made it in red, but it is not in red. So, here once again we are our hypothesis is that beta is equal to 0, this is our null hypothesis, and alpha value is 0.05. So, if p is less than 0.05, we say that reject null hypothesis. It means that for these values, that is for plasma gas flow rate and the two interaction of plasma gas flow rate with feed rate and additional gas flow rate with carrier gas flow rate are the important or are the places where our H0 is rejected. It means that the coefficients, the beta coefficients are not 0. In all other places we can say that beta coefficients are 0, it has no effect on the Logit transformed percentage anatase, and therefore it reduces the model by having only these one main effect, one main factor and the two interaction factors. Here we have once again shown it by the graphical method that if there is a systematic error because of the regression equation and then there is a random error due to epsilon. This line shows if the model was only due to the random error, all data points should fall on this line. As farther they go, you realize that these are the points of importance. Almost all points are far away here, but we have from this table we find that when you consider alpha is equal to 0.05, that is your level of significance as 0.05%, sorry 0.05 or 5%, then these are the three values which are of importance. Here it shows the main effect plots and the interaction plot. You can see that there are many interactions showing up, but we must remember that finally it is this process of rejecting the null hypothesis by comparing the p value with the pre-decided alpha is most important. This is the type 1 error. Please remember p is a p is probability of type 1 error. Just recall your hypothesis testing. Recall your hypothesis testing and regression analysis. This is an amalgamation of all of them. So, that is why we are going through a case study where you can actually see how it gets applied, each and every aspects of it gets applied. So, these are the plots. This is the analysis of variance table after Logit transformation, and as you can see here also it shows that there is the main effects are not important, this is not important. You see again here alpha is equal to 0.05 and our testing of hypothesis is that main effects, the variance caused by the main effect and the variance caused by the error if this ratio is f, which is large enough, then you say that it has an effect. Okay, the main, that is there is an effect of the main factors, the main factors. Okay. So, here what we are saying is that though there we found that plasma gas flow rate is important, here we find that main effects are not significant. Okay. So, main effects are not significant, however, the interactions are significant because this value is less than alpha, which is 0.05. This is so because it is greater than alpha, which is equal to 0.05. So, this shows that main effects, this implies that main effects or factors do not change your variation in the value significantly compared to the residual error. Whatever error is coming, the sigma, that is variation caused by the error and the variation caused by the main effect, are very similar. While this says that the error caused by the two-way interaction is more significant, is larger than the effect caused by the error. So, here again we are taking an F ratio, this is an ANOVA table. Again, if you look at our hypothesis is here is that H0 there is no lack of fit, alpha is 0.05 and this is greater than 0.05, and therefore, we say that H naught not rejected. These two are two different things. So, please remember, and therefore, this says that there is no lack of fit. So, the model that we have chosen completely defines, completely gives the explanation of Logit transformed percentage anatase. These are the confirmation to the assumption on error. So, this the first plot shows that it is a random error. This also shows that it has no effect of the what fitted values it has taken, it is also random. This is random with respect to observational order. So, there is no systematic changes because of the observations made. Here it says that there is no systematic change because of the values that we have fitted in the model, and this shows that it is actually distributed as normal because we have plotted the standardized residuals, residual error for percentage anatase, of course Logit transformed percentage anatase on the normal probability plot, and it falls on the straight line, and therefore it is normally distributed. So, our assumptions are also correct. Then as we did in the past, we have to select the levels. So, now please remember that we have to actually select only the combination because this is not important, however it is coming up. It is plasma flow rate at a high level and feed rate at a low level will give you the best percentage of anatase, and the additional flow rate at a high level and carrier gas flow rate at a low level give you the best possible percentage anatase. So, our selection is that if you separate out the interaction level, it says that plasma flow rate, gas flow rate should be at high, additional gas flow rate should be also kept at high, feed rate should be kept at low, and the carrier gas flow rate should be kept at low. With this we perform the validation runs. We find the interval for 5 validation run trials. Please recall what we had done the calculations in the past, the same applies here, and for the Logit transformed variable we find that this is the interval, the predicted interval 95% interval estimation for 5 runs with this combination of the factors. Then if you revert back, you take the inverse Logit transformation, it says that it falls from 77 to 92% interval where the percentage anatase should fall. The 5 validation trials are carried out and the average is 77.4 and therefore it falls here and therefore it validates the design. So, as such our job is done. Again we have to ask ourselves a question, is it everything okay? It should be okay. We did the, we found the best combination of factor and level to find the highest efficiency, and we found the best combination of factor and level to find the highest percentage anatase. What are they? They are given here, but if you look at it, there is a problem. Look at the problem. Here in the first case for the percentage efficiency, we are saying that keep plasma flow gas flow rate at low, while in percentage anatase we say that you keep it at high. Additional gas flow rate, here you say you keep it at low, here you say that you keep it at high. And carrier gas flow rate, it says you keep it at high, here we say that you keep it at low. So, what does it mean? It says that either you have highest efficiency of the microplasma synthesis system, or you have the maximum percentage anatase. You can't have both. This is what it really says. And that you can see here, because here if you look at the main effect plot also, you see that the slopes are in different directions. So, if you are choosing maximum on both sides, your level selections are exactly opposite. So, can we have both? We can't. Conflicting level of plasma gas flow rate and additional gas flow rate, I am not even talking about carrier gas flow rate, because in both the cases it has come only as an interaction. So, if this is the case, then you can have high efficiency, but you cannot have high percentage of anatase. So, you cannot achieve both. So, what to do in this case? The conclusion as such is that conflicting designs for highest percentage efficiency and highest percentage anatase. So, either efficiency is high or anatase is high, but not both. This is your conclusion, but in reality when you want to implement it, you have to give some solution. At least you must give some recommendation. So, the recommendation would be, let the experimenter decide. In your case, if you are the experimenter, you have to take a call whether you want a high efficiency or you want a high percentage anatase in production, and then decide what is your loss, what is your percentage loss. Generally percentage loss is defined in this manner. Suppose you decide that you want the high efficiency, then you have to know what is your loss with respect to percentage anatase. Had the percentage anatase been kept at the highest, your mean would have been mu 0. So, had your percentage anatase would have been kept at highest, its mean would have been 84.95, but now that you have decided that you want a high efficiency, you are losing your mean value from 84.95% to 79.31%. And this comes to, I am sorry, it is a negative 7%. So, I must write it down, it is negative. Okay. So, it is roughly negative 7%. So, if you are able to lose the 7% of high percentage anatase in your powder, then you will have the highest efficiency. This is what should be your recommendation. This is what should be the recommendation at the end of the complete analysis, design and analysis of experiment. So, we come to this next stage. Let us conclude the whole session of design of experiment case study. We went through it in 4 sessions totally. First question is that which process is amenable to design of experiment, we discussed that. Then we say that we must have a clear objective, we must keep the design simple, while making the objective clear we must know what is response variable and what are the controllable factors, what are uncontrollable factors, of which what is an error and what is an uncontrollable nuisance factor. We must use randomization, replication and blocking in order to control this. Randomization makes the experiment look like whatever is happening naturally in life. Replication makes sure that the error between the sets of experiment is nullified or it is averaged out. Then the blocking says that if you know that there are nuisance factors such as shift or a person working in the a person defect affecting the process, those things you block it out and keep a systematic count it also as an error factor, a controlled factor in it. Use blocks for the nuisance factor. Carry out the analysis by using the analysis of regression model and the analysis of variance together, but every time keep asking yourself, is everything okay, is everything fine. Also I would say that it is very common mistake to when you do this analysis using any of this ready-made software, then you have to control your decimal points, you have to control your significant digits, and finally never lose the overall sight of the overall picture before drawing the final conclusion. Like in this particular case, we could have drawn the conclusion in 2 cases, but then it does not really help the person who wants to really commercialize this method of microplasma synthesis of nano titania, because you said that you will have maximum efficiency for certain levels and exactly opposite levels would give you the maximum percentage anatase. In that case you have to ask him what is your preference. If it is maximum efficiency, then this is your loss towards percentage anatase. If it is maximum percentage anatase, then this is your loss with respect to efficiency. This is what we discuss. I hope you have basically learned the application of hypothesis testing, regression analysis and analysis of variance during these sessions on design of experiment. Hello and welcome back to the course on dealing with materials data. We have come a long way. We had a 6-week of course on basic understanding of basic concepts of statistics. In this session we are going to summarize whatever we have learned so far. So summing up, our journey began by telling the story about data. How to explain a data to someone who has not seen the data or data is so large that can't make out anything about it quickly. So what we called it data description or descriptive statistics. Then we started learning about chance and we defined the chance dependent events and their sample space, and then we came to the measure of chance as a probability with 3 postulates. We said that probability of any event lies between 0 and 1. The probability of a whole space is 1, and if you have mutually exclusive events, then the sum of the union of probability of union of the event is sum of the individual probabilities. And then we said that there are some sample spaces which are discrete, which tend to take discrete values, and there are some sample spaces which are continuous because they tend to take continuous values. Then we introduced what is called randomness, and here friends, I would like to tell you that after taking this course we should be able to distinguish between a randomly occurring event and an arbitrary event. You see, it is a very common habit to say that some random person came or some random thing happened. Sometimes we actually mean arbitrary. So, let me take little bit of time to tell you the random variable the way we have defined, and that is why I call it an introduction to randomness. The random variable is always connected with a probability. It is a sample space with a probability mapped to a real number. So, it is a number, but it has a probability attached to it. While when you talk of arbitrary, arbitrariness has nothing to do with probability. So, there is a distinction between the two. So, at least one takeaway from this course is definitely that you know when to use a random word and when to use a word arbitrary, how to define an event to be random and how when you say that it is arbitrary. Then we talk what are the expectations of this random variables, what is the uncertainty. By that what I mean is that what is the variance, because variance defines that it varies between these limits with certain probability, as we have studied in the interval estimation. So, the variance as a takeaway you can understand it that it is a measure of uncertainty of the random variable. Then we understood certain inequalities, Markov's inequality, Chebyshev's inequality and weak law of large number. Here what we have tried to say is we have to try to put a bound on the probability of population member lying within a certain limits. So, for example, Markov inequality says that if a random variable x is always positive, then probability that the x takes a value larger than a predefined predefined number a, it is smaller than expected value of x divided by a. Chebyshev's inequality says that the values that would lie between mu plus k and mu minus k interval of a random variable x, that is random variable x would lie between mu minus k and mu plus k, where mu is its mean value and k is any real number greater than 0, then that is less than or equal to the variance of the random variable divided by k square. The weak law of large number finally says that the sample mean comes very close to the actual mean of the population as the number of sample size gets larger and larger. This is called weak law of large number. Then we started learning about population through samples. So, we said okay, first let us see what all kinds of different distribution forms that a population can take. So, we learned about some special random variables, Bernoulli trials, binomial distributions, geometric distribution, normal distribution, negative binomial distribution, chi-square distribution, F distribution and so on and so forth. And in this we came to a central limit theorem which said that for a very large value of n, that is your large value of a large sample size, the sample mean minus the population mean divided by its population variance by square root n behaves like a normal random variable with mean 0 and variance 1. This only helps in case of a large sample size. You know that the behavior of mean is like a normal random variable and it is close, its expected value is expected to be the mean of the population. Then we said that suppose you have made this assumption on the population and your sample has certain values of its probability density function or probability distribution function, then we talked about probability plots. How to plot the hypothetical value, that is what you have assumed value of the population, along with that is assumed cumulative distribution function along with the sample cumulative distribution function, and make a judgment whether it is your assumption is true or close to the reality or not. Then we came to parameter and their estimations. We learned about maximum likelihood estimator, we learned about the estimator that is method of moments estimator. We also showed that there could be inconsistency if you use method of moment estimators. The evaluation of parameter estimation also we learned. We said that there could be, you can take a least squares distance, minimum bias distance, and then if there is no bias, then you call it an unbiased estimator. And we also introduced very briefly the Bayesian estimation. We did not really introduce Bayesian estimators per se, but we gave the conceptual design of how the Bayesian estimators are derived. We moved forward and we started working on hypothesis testing. Now here I would like to tell you that yes, we did all the work by looking at or making an assumption that the population is normal. So you might be wondering that if the population is all the time normal, then what is the point, because it was already said that the materials data tend to be skewed, they are not beautifully bell shaped curve, then what is the point of having it. But I would like to bring it to your notice that the concept of critical region, the concept of type 1 and type 2 errors, and the approach to keep the type 1 error as small as possible by predefining a value alpha, this concept has nothing to do with any distributional assumption. These are very general assumptions that have been made. So these are the assumptions for any distribution. There is no assumption, there is no need to have a normal distribution assumption here. Also with respect to testing the mean equal to a given value or equality of two different means, or when the means are equal when variance are unknown, to say that a variance is equal to a given value, you take any of this test, which will be a z test, a t test or chi-square test. If you wish to have a look at the table and arrive at an alpha value or to arrive at a cutoff value, then you need a normal distribution assumption. Otherwise, frankly speaking, two-sided test says that zt or chi-square neither should be too small nor it should be too large. The value, you can always calculate the t or chi-square, and you just have to see that it should not be very large, and it neither should be very small if you are looking at two-sided test. If you are looking at one-sided test, and depends on which side you are looking into, it should not be very small or it should not be very large. And this we demonstrated by arriving at Weibull T and Weibull chi-square test. So here I would like to tell you that the real takeaway for you is to understand that this statistics, the Z statistic, T statistic, chi-square statistic, and in future in ANOVA what comes as an F statistic, their value comparatively is large or small is all you are looking at. If you wish to have what we call a cutoff value, then as we have shown in the case of Weibull distribution, you can always do it by doing the simulation. Now the computer is in your hands, the algorithm is there, you can simulate the random numbers and generate the cutoff values that you wish for any given alpha value that you need to have. So, the takeaway here is, please do not get carried away by the normality assumption. The takeaway is that these statistics which have been introduced here with the reference to the test, the hypothesis made, are valid even beyond the normal distribution. Then we started going into applications. We first considered regression application. We again looked into the coefficient estimation, and then we did the hypothesis testing for regression coefficient, mean regression and future response. Again, please remember, in all this we have derived t statistic, and t statistic is a t statistic. It need not have the normal assumption. It is a unitless statistic and can be looked into it with reference to any distribution that you wish to assume, or you can do it by simulating it and getting the cutoff values if you are so keen to look into it. Otherwise, looking at the largeness and smallness is good enough to give you an answer. Then we talked about coefficient of determination to decide how good is the fit. We talked about residual analysis, very important. We have made some assumptions, and these assumptions we must verify through the residual analysis. We also talked briefly about the transformations that can lead again back to regression, linear regression, and I know that in the sessions doing your analysis with data analysis with R, you have been given variety of examples other than the what we discussed in the our regular statistics class for this kind of transformation leading to a linear regression model. We very briefly talked about logistic regression. Then we started going through the case study and understanding analysis of variance. We studied the analysis of variance. Again, we came across the F ratio, because we realized that analysis of variance, as it says, it is comparing the two variances which arise under the hypothesis and due to the error. And if you compare the two estimate of variances, it leads to an F ratio, and larger the F ratio, more chances that you are deviating from your assumption of the rows, or all the laboratories. In our case of case study, all the laboratories are not different, or all the laboratories are same. So, you are deviating from it. Once again, F distribution is not important, F ratio is important. We extended it to a two-way analysis of variance, and now you can all imagine that you can further extend it even to the three-way analysis of variance and so on and so forth, depending on the problem. Finally, we came to design of experiments. This we understood completely through case study. There is one important point which I had forgotten to mention, which I would like to mention it here, that when we chose the design matrix of size 16, please remember, had we not done this exercise, since we had 7 independent random variables varying, that is independent variables varying were 7, the size of the design matrix would have been 2 to the power 7. Instead, we worked out with 2 to the power 4. So, this is also called a fractional factorial experiment. This is confounded experiment, I totally agree. But these details, as I said, are the details when you go into more and more understanding and detailed or very intricate designed experiments. But to begin with, because this says that dealing with materials data, to begin with, when you want to do the design of experiment, this case study gives you an idea that instead of having experiments number of the power 2 to the power 7, we are dealing with only 2 to the power 4 and that makes the difference.